So I'm Cristina Lo Celso, and I'm really delighted to see so many of you here today. So my background really is in biology and biotechnology, and what I have been doing for a long time at Imperial College, and now more recently having joined the group at the Hammersmith Hospital as well, I have been interested in blood stem cells. So we call them hematopoietic stem cells. These are the stem cells that maintain all blood production, including the production of all red blood cells. They're very rare cells that are contained inside the bone marrow, and they can only perform their function because they are in the bone marrow surrounded by a microenvironment that is very complex and we don't fully understand yet. So I have spent many years looking at hematopoietic stem cells using the mouse as a model organism, so something very far from what Julie has been doing in the meantime. However, for example, using a number of approaches, such as, for example, intravital microscopy, we have been able to see where hematopoietic stem cells are. Actually, this is a very relevant example because this is the progeny of stem cells that had been injected in the mouse about 2 days earlier, and this is an experimental model of hematopoietic stem cell transplantation that we use. So we can see in the mouse how hematopoietic stem cells go to the bone marrow very quickly within minutes, and they give rise to progeny, and they do so by having some very specific types of interactions with the microenvironment that is around them. And for example, one of the questions we have related to gene therapy is very well to modify the stem cells and transplant them back in, but will they find the right soil where they can then really perform the function that they need to, that we need them to do? Now we're going to have the same adventure as Julie. Oh, here we go, and you can see they actually wiggle. This is something we could not see in humans, but we can see it with the mice, and I suspect the human stem cells will probably do the same. More recently, we also started looking in doing a lot of analysis of bone marrow tissue ex vivo, and here I'm still showing you an example of a murine bone marrow sample. This is bone marrow contained in the vast majority of a tibia of a mouse, and then below you can see a couple of areas just blown up at a higher magnification. And in this study in particular, we are interested in macrophages. Macrophages are the cells in yellow here, and you can see how there are very many in the bone marrow. And we know that a good proportion of these macrophages, for example, are the ones that are involved with the red blood cell production. And again, understanding how these interactions happen in the context of a number of red cell disorders, including sickle cell disease, is going to be very interesting. And by talking to Julie and some colleagues more recently, I'm really understanding how little still we know about erythropoiesis in situ, even in healthy humans, and let alone in situations where we have diseases occurring. Now, I'm not here just to show you images of mouse bone marrow, because lately we started looking at human bone marrow as well, and this is why being based here at the hospital is fantastic. Because of my long-term interest, we started by looking at samples that come from patients that had acute myeloid leukemia, but we could very well look at samples that come from patients with an array of other different diseases. And again, we could start and understand, for example, how erythropoiesis happens in situ in humans. So the reason to be here today is that I think it is a very exciting time in history where we can see a lot of scientific progress happening. And we can start putting together the things that we've been learning from the biology side and the things we're learning through the clinical perspective. And we can put them together to create something bigger and really make a difference for patients for the future. So here within the Center for Haematology, we have a number of initiatives running. And again, to keep the theme of erythropoiesis, we have sickle cell disease clinics where Stephen Okoli is working, for example, and it's always a pleasure to work with him. Julie already mentioned Josu de la Fuente's trials for gene therapy. We are also a bone marrow transplant center of excellence with Eduardo Lavaria and Andrew Innes. We have Dina Iskander studying diamond black fan anemia. And so we are really collecting a lot of clinical and scientific expertise on human erythropoiesis. And this goes also beyond Imperial College. And again, this is thanks to Julie's work here. And it really has been such an honor to host her here for this year. We can go well beyond the walls of Imperial College. With Julie and Lucio Luzzatto in Tanzania, we can look at sickle cell disease and malaria epidemiology put together. We can think about mechanisms of the disease and treatments. We have been working with David Kent in York and David Williams in Boston in the US, looking at the genomics of sickle cell disease patients pre and post gene therapy. And also we have collaborations with John Strubulic at King's College London, and I think John may be online, so thank you for joining. Oh, here, you made it in person, fantastic. Even better, see. And with him we can really tackle healthy and sickle cell erythropoiesis. So there really is a growing consortium that spans across many sites. And the aim really is to understand healthy and sickle cell disease erythropoiesis, but also erythropoiesis in other conditions and human hematopoiesis in general, so that we can improve treatment. And I guess today the sickle cell disease is really one of the exemplars that we can have. But what we want to do is to improve treatment for patients. We want to deliver better treatment, more effective treatment, curative treatment, really, with the long-term goal of really developing in situ gene therapy, and to do this globally. And you've heard from Julie the struggle, but also the importance of making hydroxyurea available to everybody globally. Imagine if we could make gene therapy something as simple as hydroxyurea that we really can make available globally to everyone. And it's exciting to put together all different points of view. That was it.
Thank you very much. Okay, thank you very much for that. I suppose we could take one question. If there's a question in the audience. I did ask you up before to keep you. Is there anyone online? Okay.
I have a question.
Thank you.
Yeah.
Yes, very nice presentation. Thank you. I'm Sarah Elhas, postdoc from the Strubulic lab. I wanted to ask you what exactly is your plan to do with respect to looking at erythropoiesis in sickle cell? What aspect are you planning to study?
Well, there are several questions. Just this morning, we were having a discussion talking about, understanding where hemolysis happens, for example, whether inflammation linked with hemolysis ends up affecting hematopoietic stem cells. I have been looking for a number of years at how severe infection and chronic inflammation affect overall hematopoiesis and lead to a reduced ability of the stem cells to generate the erythroid lineage, for example. And so I think it will be very important to understand whether there is a sort of like a spiral effect and a link between the diseased red blood cells being produced, being lost, causing inflammation, and that eventually leading to further issues. It is very possible that through chronic inflammation, we are affecting the stroma in the bone marrow. The stroma are the non-blood cells that support the production of blood cells. We know that in hematological diseases, the stroma ends up being severely compromised to the point that it no longer supports healthy hematopoiesis. And this is, of course, a very extreme case. And there is evidence from sickle cell disease that the stroma is still recoverable, but there are differences between patients. And so it's really through partnering with people like you guys, we can start really looking into the details of this and figuring out how to tackle it and how to fix it, really.
Thank you very much.
Thank you.
Thank you. Okay.